In this video, we're going to talk about something called exponential functions. Exponential functions are functions whose equations contain a variable in the exponent. So when you look at this function down here, f of x equals 2 to the x power, this is called an exponential function because the variable that we'll be plugging into in place of x is the exponent. Now, I have not changed my notes in several years, but you'll notice the explanation says here, many real-life situations including population growth of epidemics. So this idea of what you're hearing about, you're talking about in the news right now, flattening the curve, all of this is actually tied to the mathematical notion of an exponential function. An exponential function, when you look at the graph, starts out kind of flat, but as you move to the right, it starts to increase very quickly. You will see this idea, this picture, represented in several different websites. If you look at confirmed coronavirus infections, you'll see that the curve is kind of flat, starts out kind of flat, and then starts to increase and go high really quickly. Here's another idea of that. When we talk about flattening the curve, this idea is we want to keep that graph from getting really high really quickly. So the more flat we can get it, the less deaths, the less infections there are. We don't want that graph to go exponential. An exponential graph goes really high really quickly. So you notice that all of those pictures look a lot like that picture that we have in our notes for an exponential function. So here, you look at the red dots, it gets really tall really quickly. That's an exponential function. Our goal when we talk about flattening the curve is to kind of break out of that cycle of an exponential function and have less infections. So when they talk about that, really talking about an exponential function, exponential growth. Okay, so an exponential function actually does model very accurately the growth of epidemics, population growth, radioactive decay, and all kind of real-life applications. So what is an exponential function? An exponential function is a function that has a variable in the exponent. The number that comes right before, in this example it's a 2, is called the base. So in this case 2 is the base. So when we're talking about exponential functions, we have an x value that's going to go into the function, and we have this number that's going to be the base, and then our variable will be the exponent. And that exponent, that variable, that x, that's what's going to change. The base itself for the entire function will always stay the same. And we're going to see an example of that in just a minute. We have some restrictions on what the base can be. The base must be positive. So we're not allowed to have a negative base. The base must be positive. The base can't be 0. And it can't be 1. So when I give you an exponential function, it will always have a positive base, and the base will never be 0, and the base will never be 1. So let's look at an example of an exponential function. F of x equals 2 to the x power. I have a little table here, and in this table I have a list of x values. Sometimes we call this a t-table. But we have a list of x values that we're going to plug into this function in place of x, and then we're going to get some y values out. Now for all of these, the base itself is going to be 2. So I'm just going to copy in a 2 all the way down in the y column, because that's going to be the base. The exponent is what's going to change based upon x. So if I say x is 3, then now 3 goes to become the exponent on that base of 2. If I say x is 2, then 2 becomes the exponent. If I say x is 1, then 1 becomes the exponent. So the x values that I have are going to change the exponent on that base of 2. So the base is not going to change. Now the exponent, it's what's changing as I pick a different x. Now the first several answers that we get are going to be pretty straightforward. What does it mean to do 2 to the power of 3? Doesn't that mean 2 times itself 3 times? 2 times 2 times 2, I get 8. So we want to plot the point on the graph, 3, 8. So remember, our ordered pairs that we plot are x, y's. The x value that went in was 3, the y value that came out was 8. So we're going to make a little extra column here for the ordered pairs. When I go to my graph, find an x value of 3 down here, a y value of 8 up here, we can plot that point. Now officially there's an arrow here, so I'm going to go ahead and just put that arrow there while we're up there. We can choose any x value that we want. It could be 4, it could be 5, it could be 6. So the x value that we choose could be larger than 3. I just chose 3 as the largest because I can't be here for the rest of my life plugging in x values. So I chose 3 as the stopping point, but officially the graph continues on past an x value of 3. Alright, let's look at a different point. If I have an x value of 2, it becomes the exponent on the base of 2. 2 squared, or 2 times itself 2 times. I get 4. So 2 goes in for x, a y value of 4 comes out. 2, 4. Okay, 2 to the power of 1. 2 to the power of 1 is just plain old 2. So if I put in an x value of 1, we get out a y value of 2. Now here's where things start to get a little bit more interesting. We might have to come up with some new rules. Let's go ahead and just write new rules. Okay, we're going to learn something new here. What does it mean to take a base and raise it to the power of 0? So we're going to call this our 0 exponent rule. Okay, the 0 exponent rule says anytime you take a base and you raise it to the 0 power, it doesn't matter what the base is, but any base raised to the 0 power, the answer is always exactly 1. So 2 to the 0 power is 1. So an x value of 0 goes in, a y value of 1 comes out. So I'm going to plot the point 0 for x and a y value of 1. So make sure that you have that 0 exponent rule written down. Alright, now the next one is even more interesting. We have 2 to the power of negative 1. What does it mean to raise a base to a negative exponent? So now we have a new rule. We're going to call this the negative exponent rule. Okay, the negative exponent rule says if you have a base raised to a negative exponent, so I'm going to put negative with a little number there, this is always going to be equal to the reciprocal of the base. So you can think of it as flipping that fraction. Think about this as base over 1 and then flipping that fraction. Reciprocal means to flip. Think of it as a fraction and then flip it over. So if I have some base raised to a negative exponent, some negative number in the exponent, we're going to flip the base and then we're going to take off the negative on the exponent and leave it as just a plain old positive number. Okay, this is our negative exponent rule. So what does this actually look like? Well, we have 2 to the negative 1 power. We're going to rewrite this as, think about this as 2 over 1, and we're going to rewrite this as 1 over 2. So the reciprocal of 2, we're going to think about that base as 2 over 1. Think of it as a fraction. Flip the fraction, so we get 1/2, and we're going to raise that to the positive 1 power. So we end up getting 1/2. 1/2 to the positive 1 power is 1/2. So negative 1 goes in for x. The y value that comes out is 1/2. So we end up plotting that about right here. It looks like about a y value of 1/2, x value of -1, -1, comma 1/2. So 2 to the -2 power. Since I have a negative exponent, I'm going to rewrite the base as the reciprocal of 2, which is 1/2. Raise that to the positive 2 power. Square the top of the fraction. So 1 times 1, or 1 squared is 1. Square the bottom of the fraction. 2 squared is 4. We end up getting 1/4. -2 goes in, 1/4 comes out. I can plot that point about right there. -2, comma 1/4. 2 to the -3 power. I'm going to flip the base. My base is 2, but I'm going to flip the base, write the reciprocal of the base because I have a negative exponent. The exponent changes now to become positive. Cube the top, so 1 times 1 times 1 is 1. Cube the bottom. 2 times 2 times 2 is 8. So 2 cubed is 8. So our order pair that we're going to plot is -3, comma 1/8, which is about right there. Okay, so this graph right here models exponential growth. We're going to put a little arrow here again, since we're over here by these points. We're going to put a little arrow because officially the x values could be -4, -5, -6. They could continue toward the left of the graph. So a couple of observations we want to make. One of the things I want to mention here is the domain of an exponential function. The domain of an exponential function will be -infinity to +infinity. The x values that we're allowed to put in can be negative, they could be positive, they could be 0. You can really have anything you want to for an x value that goes in to an exponential function. So all of these x's are allowed. Positives, negatives, zeros. We can have anything we want to go into the function. Also, you're going to see that you would always have an arrow that points to the left and an arrow that points to the right. It's all real numbers for the domain. However, the range is a little bit different. The range is actually always going to be from 0 to infinity, but does not include 0. These are the y values that come out. So what you're going to notice is as you pick these x values and you put them onto that in that exponent for that base, if the base is positive, you'll notice that all of the y values turned out to be something larger than 0. So it didn't matter if our exponent was positive or if our exponent was negative or 0. Notice that all of the y values turned out to be something that was greater than 0. And that's going to happen every single time. And in fact, we never got out a y value. We never got a result out for any of those that were 0. And if you look at the graph, you'll notice the graph itself seems to hover right above the x-axis. Never actually dipped below it. So we never actually crossed the x-axis. We never dip below the x-axis. So the y values that we get out from an exponential function will always be from 0 to infinity, but never including 0. So when you look at the very bottom of the graph, we hover right above the x-axis, and then we go to the very top of the graph, and we're going to see that arrow. Oops, sorry. We're going to see that arrow. Okay. Turns out that the x-axis in this case is a horizontal asymptote. So you'll notice that the graph gets really close to that x-axis, but doesn't ever actually cross it. So the horizontal asymptote for an exponential function is that x-axis, or the line y equals 0. Is this a one-to-one function? The answer is yes. You'll notice that it passes the horizontal line test. So any horizontal line that I draw is only going to cross through once. And what does it mean if we have a one-to-one function that passes the horizontal line test? That means that this exponential has an inverse function. And the inverse function is what we're going to talk about in the next section. What does the function look like that does exactly the opposite of this exponential function.